there any questions? Okay, if not, we'll continue with the discussion of curvilinear coordinates, specifically the cylindrical coordinate system, which may be defined with respect to the rectilinear coordinate system in the following way. This is the point x1. The cylindrical coordinates, the three coordinates are defined as follows. This is the coordinate RC, where distance from the origin of the projection of the point onto the 1-2 plane, that is RC, and this is the angle that it makes with the O1 axis or the x-axis, if you wish. And then the third coordinate is nothing but the O3 axis itself, that is the same as the ZC axis. So analytically, it can be expressed as x1 is equal to RC, the cosine of the angle phi. x2 is equal to RC sine the angle phi, and x3 equal to ZC. The three coordinates U1, U2 and U3 are RC, phi and ZC. One of them is of course equal to x3. So conversely or inversely, the three coordinates RC, phi and ZC may be expressed in terms of x1, x2 and x3 as RC equal to x1 squared plus x2 squared raised to the power of half. Phi may be written as tan inverse of x2 by x1, and then ZC can simply be equated to x3. This is the cylindrical coordinate system, and we, based on these two equations, we can construct the tangents, or rather the tangent to the coordinate lines and the normal to the coordinate surfaces. If you do that, you will find that they are proportional to each other, and that is because of the fact that this is an orthogonal system, orthogonal coordinate system. You can easily construct the orthonormal coordinate system and dispense with the two separate set of basis vectors, which are reciprocal actually. Here they are proportional to each other, and so finally we arrive at ERC is equal to and then phi is equal to minus sin phi E1 plus cos phi E2, and then EZC is equal to simply E3. We arrive at one set of basis vectors. The crucial point here is that these two basis vectors are dependent on the angle phi. That means this transformation is not linear but non-linear. Whenever you have a linear transformation, the coefficients relating the two sets of basis vectors will be constants. That is, comes from simple rotation of the rectilinear coordinate system. Here we have a curvilinear coordinate system, which means that the relation of the basis vectors in the two sets are related, right? And the coefficients that relate them are actually dependent on the coordinates themselves. Here, of course, it depends only on the coordinate phi. More generally, we could have all the coefficients depending on the coordinates of the point, right? So we can then invert this and obtain the inverse, which will also be useful. We have E1 when it's equal to, we can get our inverse relations that we wrote down in the previous class. And E1 will be ERC cos phi minus phi define this. And then E2 is equal to ERC sin phi plus E phi cos phi. And then E3 is equal to EXC. So inverting this is very easily seen. E1 dot ERC from here is cos phi, so we get that E1 dot E5, right, is minus sin. So you can easily by this inspection write the inverse relations, right? We will need that. Now the derivatives of, because we are going to discuss how the gradient is to be constructed, and all the operations involving the gradient operator will necessarily involve the derivatives of the unit vectors here with respect to phi alone, right? That can be easily calculated, right? So we get ERC by d phi is equal to minus sin phi E1, right, plus cos phi E2, which is nothing but E5. So very simply, that can be obtained, right? The derivative. We'll see where these derivatives are useful. Similarly, the E5 by d phi is minus cos phi E1 minus sin phi E2. That's simply the negative of ERC. All other derivatives with respect to the coordinates of all the unit vectors are zero. ERC, there is no dependence on RC of any of the unit vectors, right? And there is no dependence on ZC also of any of the unit vectors. So these are the only two derivatives we have to consider. So as I pointed out, as we go along the construction of the gradient and various other operations involving the cylindrical coordinate system, it's important that you repeat the same for the spherical polar coordinate system, which I will now define. I am not going to do the derivation. The spherical polar coordinate system. Now, the spherical polar coordinate system again is defined with respect to the Cartesian coordinate system. So I take a point, let's say x1, and then we can ask how these rectilinear coordinates are related to the spherical polar coordinates. So that is defined like this. Again, we have the point here. The phi is again a part of the spherical polar coordinate system. However, the distance RC is no longer a spherical coordinate, it only comes in the cylindrical coordinate. This R is one of the coordinates in the spherical polar coordinate system. That is simply the distance of the point from the origin. That is, we call as R, right? So that's why I am not calling this as R. This is called as RC. The R corresponding to the cylindrical is clearly not the same, right, as the R, unless the point is in the xy plane or the 1, 0, 2 plane, right? So in general that is not true. Now the other coordinate is this angle that this line makes with the z axis. That is what is called as theta. That's the new angle coordinate that comes in the spherical. So in fact, except for phi, all the other coordinates are different. Two other coordinates are different. So clearly, we can define the spherical polar coordinate in the following way. So now x3 is the easiest to write down. It will simply be r cos theta x3. That is the relation between the r and theta and x3. Now, r sin theta is nothing but rc. That's the other projection on onto the plane, right? This is RC. We are not going to use that. That is equal to R. That's the relation between the coordinates of the cylindrical coordinates and the spherical polar coordinates. So this is R sine theta, right? So clearly, then x1 is R sine theta cos phi, and x2 is R sine theta sine phi. This is RC. We replace this by RC, right? And then don't do anything with this. Then I get the recover the cylindrical coordinates. Right? So anyway, you don't have to consider the relationship between the two. This is one. This is another that we will be considering. Right? So clearly, then the other inverse relation can easily be shown to be x1 squared. R would be x1 squared plus power half the phi is the same. So phi the same coordinate. So not surprisingly, that can be expressed simply in terms of x2 by x1. By tan inverse of x2 by x1. And what about theta? Theta can be written as in many ways, but I can certainly write this as cosine of x3 by r, which is square root of so that is one way of writing the inverse relations. One, we have x1, x2 and x3 in terms of r, theta and phi. Other one gives r, phi and theta in terms of x1, x2 and x3. So again the same procedure will apply to get the a1, a2 and a3 from this, or b1 and or b1, b2 and b3 from this. But you will again find that you look at calculate either one of them, you will find that they are orthogonal to each other, not orthonormal. Orthogonal. So we will construct the two sets of basis vectors by different methods, either directly by calculating the tangent to the coordinate lines and the normal to the coordinate surfaces, which I would recommend as exercise. On the other hand, you can also take one of them and obtain the other, either by taking the inverse and the transpose, or because they are reciprocal to each other, or by again using the reciprocity property by using the cross product relations, right? And so you can use either one of them. So I leave it as an exercise. The final result, though, I will write it down, so available in here. Of course, we have no problem with the notation in any of the cases. So I'll write down the final result. ER is sin theta times cos phi ex plus sin phi ey plus cos theta ez. Oh, I'm sorry, E1. And then E5. So looking at this, it's always good to compare, right? So ER, now you can easily recognize this as ERC. Coming from this, R sin theta, so you're also getting the same, ERC sin theta. So there's a relationship between the cylindrical and the spherical, and E5, there's no surprise that we get the same result because the phi is the same. So the unit vector corresponding to that turns out to be the same, right? And then again, this is again ERC, but then it has another component coming from EZ. So these are the two new unit vectors, and importantly now, all the three unit vectors are dependent on the coordinates. These two on both theta and phi, right? And this on phi alone. So this is very easy to write, but however, again, we won't be equal to this. Of course, equal to minus ERC, but we need a relationship between this and so we need basically dER by d theta, dER by d phi, right? And then d theta by dr, d theta, and d theta by d phi, and on top of it d phi by d phi. You will find that all of them can be expressed as a linear, as a combination of the unit vectors themselves. I don't have the results with me here. They are readily available in Wordsworth, Lightfoot, or any other standard textbook, but we visit this again towards the end. Once we have completed the cylindrical coordinate operations, we come back to spherical polar. But you should attempt to differentiate and find out how the resultant vectors can actually be expressed in terms of the unit vectors of the spherical polar coordinates. That's what we need. What I'm saying is that we need relations very similar to these for those derivative also. I'll leave that as an exercise for now for you to do. Let's get back to some of the basic operations in the cylindrical coordinates. We've already seen that, for instance, when I have a dot product like this, because of the orthonormality property of the cylindrical coordinate system, many of the relations involving simple dot product of vectors or even tensors would be very similar to what we had for the Cartesian coordinate system. So, for instance, this we wrote as AIEI. It basically follows from the fact that I can write this as A1 E1 plus A2 E2 plus A3 E3. Then we have the dot product of the being written like this, and then you can easily construct this if you have the relationship between the unit vectors, the dot product of the various unit vectors. Now, because this is an orthonormal system, you can easily show that ERC dotted with ERC is equal to 1, ERC dotted with E5 is equal to 0, and so on. Because we actually already verified the orthogonality, and then we said of the A's and the B's, and then we constructed these by making the A's and B's of unit norm, and we have one set of unit vectors, basis vectors, which have unit norm. So clearly, then I would have this simply take the following form. It would be ARC, right? ERC plus A5, B5. Plus AZC, BZ. So when the components of two vectors are expressed in terms of cylindrical coordinates, the scalar dot product will be the same. Now, what about the cross product? Now you can easily verify. Now, for instance, there is a slight difference in the way I approach the operations in the rectilinear coordinate, as opposed to how I am going to do it for the curvilinear coordinate. The rectilinear coordinate, I got a group of terms like A, I, B, I, and I said you can recognize it as the dot product of the two vectors. I did this in each and every case. I got some group of terms such as dv1 by dx1 plus dv2 by dx2 plus dv3 by dx3, and I said you take this as the divergence of the velocity vector phi. Here though, so I didn't really define operations involving the unit vectors, right, directly. I sort of said said that this is how it will be. And clearly, the operations involving the unit vectors can be easily obtained from this. But strictly, I should have gone the reverse way. That's a more fundamental way. Define the operations involving the unit vectors or even the unit tensors, and then conclude what it is for arbitrary two vectors. For instance, A cross B, I simply said this is defined as E1, E2, E3, A1, A2, A3, B1, B2, B3. Strictly, I can do the same thing here, write A in terms of this and B in terms of this, and let us say if I take the cross product, then I should be able to get this, provided I define what are the cross product of the unit vectors among themselves, right? So clearly that you now know that that is E3 and so on. And E1 cross E1 would be 0. These are all vectors, right? And so on. Now, how would you do the same thing for the cylindrical? Now, the cylindrical, because again of the orthonormality property, these operations will look very similar. You can easily verify, for instance, that ERC cross ERC equal to 0. Here ERC cross E5 is equal to EZC, right? So the cross product with itself is 0. So I am going to write only the cross product with respect to other vectors. So ERC cross E5 equal to EZC, right? And similarly E5 cross EZC is equal to ERC, and EZC cross ERC is equal to E5. These you can easily verify. Without there is a doubt, right? All you have to do is I know these in terms of E1, E2 and E3, and I know the relationship between the cross product of E1, E2 and E3 with the various vectors. I can easily prove if we take this as given, right? And then, so obviously the cross product will also have the same form, ERC, E5, EZC, ARC, A5, AZC, and so on. You can easily verify that and be written like that. So what about operations involving a tensor and a vector? So what I am now considering are vectors which do not involve the gradient operator, because that is when we have to consider the derivatives of the unit vectors also. These are all operations that do not involve that, right? So I will consider all those operations separately. Now what about, we had two important dot products of a tensor with a vector. One of them was the second order tensor, A dotted with A. So again, I simply define the ith product of this as Aij, Aj, and similarly, now strictly, if I want to follow the same route of expressing the vectors in terms of the unit vectors and then defining the operations involving the unit vectors, strictly I should have done this by introducing what is called as a unit tensor and then defining operations involving the dot product of the unit tensor with the unit vector. I didn't do that. There was a reason why I didn't do it that way. So now, if I want, because that procedure will become very important and almost necessary when you go to some of the operations involving the curvilinear coordinate system, right? So here, the unit tensor, right? There are, just as there are 3 unit vectors, there are 9 unit tensors in the rectilinear coordinate system. For instance, the 9 unit tensors are E1, 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 E2, E1, E3, and similarly, we will complete the other 6. Right? Now what is E1? E1, we already know how to write the ijth element, and in fact construct the entire tensor of a vector like this. Ijth element is simply aibj. Right? So now what do you think is E1? E1? The unit tensor E1, E1. What will it look like? 3 by 3 matrix, if I want to express it. How would it look like? It's not identity matrix. One. There will be only one element which would be 1. All other elements would be 0. So in fact, if I have, for instance, a 3 by 3 matrix, if I want to write it in terms of the unit tensors, this is what I mean. Clearly, all of you will understand if I write it as A11 and 1 0 0 0 0 0 plus A12 and 0 1 0 plus so on. You have to write 9 terms. So each of the terms in the matrix, the 3 by 3 matrix, right? I can write it as the product of that coefficient times a unit tensor. This is exactly what I mean by a unit tensor. So a tensor, right, just as I would write a vector as A equal to AI EI in the repeated index summation convention. Similarly, a tensor would have to be strictly written as Aij EIEj. That will give you the full tensor. This is the alternate way of writing the tensor. Any arbitrary second order tensor can be written like this in terms of the unit tensor. Now let's get back to the product like this. Right? If I want to do it properly, starting from the basics, I write this as Aij EIEj. I want the ith component, so I won't use this. So I simply write A. Let's make this. Let's look at the. Let's write it like this. Let's see what we get. Ej, right? I'm not particularly the ith component. Let's write the tensor like this, right? And take the dot product with, of course, here I have used I and j. I use Ak, Ek. Right? So once you have accepted this, right? We already know this. This is how I would actually write it in terms of the unit vectors and the unit tensors. Now, this is actually further, it can be written as Aij, Ak, Ei, Ej dotted with Ek. So now I have to define what these are. Ei, Ej dotted with Ek is actually will turn out to be Aij, Ak. So it's very easy to write this. This is a tensor dotted with a vector, right? Unit tensor. It will simply turn out to be, all you have to do is to take the Ei out, and it will be simply Ej dotted with Ek, and so that will be Ei delta Jk. Very easy to remember. Ei, Ej dotted with Ek is just, consider this as Ei times the scalar Ek dotted with Ek, which we know to be delta Jk. Right? So what do we get now? So this would be, I have put Aij, Aj, Ei. I can then clearly infer the ith component of A dot A to be Aij, Aj. Right? Which is what we sort of introduced directly. So now what you have to remember is this important is equal to EI delta JK. Now you can easily verify that for the cylindrical coordinate system also a similar relation. You can see now the point is that this would be 0 unless J is equal to K. And then you have the vector EI. Separate out the vector that appears. So the order is very important. Order is very important. It will be totally different if you have EJ, EI. EI, EJ dot EK. Now this is, none of the indices are repeated, right? So I can form a tensor, a vector which is a dot product of a tensor with a vector. I can choose from any of the three vectors. This can be 1, 2 or 3. This can be 1, 2 or 3. This can also be 1, 2 or 3. So all possible combinations are allowed. And this formula gives the answer for all possible combinations. Clearly from this, if J is not equal to K, it would simply be 0. J is equal to K, it would simply give me the vector EI. That's all there is to it. Right? You can easily verify, for instance, you can easily verify that ERC dotted with, right, let us say E5. What do you think this would be? Just guess. You can easily prove that this will be actually equal to 0. Because this would simply be, same formula would apply here. This would be E. And so this is 0. This is 0. Right? Similarly, for instance, E5, let us take ERC dotted with ERC is simply equal to E5 and so on. Right? So given any combination, you can simply look at the two vectors that are forming the dot product right next to each other, and if that is the same, right, then you get 1, and then the vector is that is behind is always there. Otherwise, it would simply be 0. So what would happen is all these operations also. So now a tensor would have the following form. In terms of, if you want to express a tensor, I will simply write RC phi ZC. RC phi ZC. So this first element now would be ARC RC. This would be ARC phi and so on. The dot product of this with another vector, right, which is also expressed in the cylindrical coordinates, can simply be obtained. We already pointed out that this operation is very similar to what you know already. It's simply the multiplication of a matrix with a vector, right? So you can do the same thing in the cylindrical coordinates also. Simply get, this is again a vector. That vector will simply be given by multiplying the matrix with the vector. It can be done. You can easily verify this by verifying these relations. We have already verified, in fact, the tensor, relation will remain the same. The relation between the unit tensor dot product and the unit vector, that would remain the same. Here, it's the inverse operation. The vector comes before, so I need to specify what this is. I dotted with a tensor. The vector dotted with a tensor. I pointed out that this is simply like pre-multiplying the tensor by the transpose of the vector. That's what you will get. You get the transpose of the vector you need. Right? So this again can be easily shown to be simply delta Ij Ek. So these now define the dot product of unit tensors with unit vector or unit vector with a unit tensor. So these will give you all possible relations. So again, by substituting the tensorial form of A into this, in the vector form of the small a, you can easily obtain, right, these relations by a way similar to what I have done here. Right? So these different, again the same principle will apply to the cylindrical coordinate, primarily on the account of being an orthonormal basis set. So all of these operations will carry over, right? And whatever you did in the rectilinear coordinates, you will simply do in the cylindrical coordinate. So something like this we require when you want to calculate the stress vector, for instance, right? You have to take the normal of T dot N or N dot T, both are the same for us because the stress tensor is symmetric. Right? Now I can do the same thing in the cylindrical coordinate, whichever I want, right? Express the normal in terms of the, if I want this, for instance, express the normal in terms of its cylindrical coordinate components, right? And the tensor in terms of cylinder, simply multiply one by the other, you will get the vector in the cylindrical coordinate system. And this is possible because these operations involving the dot product of a vector with a unit tensor or a unit tensor with a unit vector carry over to the cylindrical coordinates. Are there any questions? So these are not the complicated issues. The complicated issues are when we have operations involving the gradient. Right? So we take up how to express the gradient of operator first. With the gradient operator, we have a whole range of operations. The gradient of a scalar, the gradient of a vector, the divergence of a vector, the divergence of a tensor, and so on and so forth. Right? So we'll take that up. How to express the gradient of operator, or rather the gradient operator in cylindrical coordinates. The procedure is fairly straightforward, although there are some similar methods available. I follow the method in Wordsworth Lightfoot because conceptually it's very simple. Although for implementation it's a bit tedious. Now we know the gradient operator in the Cartesian coordinate system. For the Aris what I need, but anyway, so the point here is that now what I want is I want this as ERC times something plus E phi times something plus EZC times something. That something should involve derivatives, right? With respect to RC, phi and ZC. So basically, you know, the gradient, it's easier to, rather than look at the gradient as an independent operation, it's convenient to look at this as something that is operating on a scalar phi. Of course, the gradient can also operate on a vector, and that will become a bit complicated in the cylindrical coordinates. Now, here though, the phi is expressed in terms of x1, x2 and x3. That is when these derivatives make sense. So obviously, if this something is to have derivatives with respect to RC, phi and ZC, that means the same phi, the skip, we have to call it psi. The phi appears as a coordinate, so I am now calling the scalar psi. In this case, it is a function of x1, x2 and x3. Here, of course, the same sign would have to be expressed in terms of RC, phi and ZC. So now, I have already written the expressions for E1, E2 and E3 in terms of ERC, E5 and EZC. So all I have to do is to express the operations d by dx1, d by dx2 and d by dx3 in terms of d by drc, d by dzc and d by d5. If I can do that, I just substitute it there and then carry out the algebra and then I will get what I want, right? So basically, if I want d by dx1, I want this expressed in terms of d by drc and so on, will depend on all. So what I am actually looking at is, this is of course x1, x2 and x3. what I am looking at is d by dx1, but phi, if I want to relate this derivative with the derivatives with respect to rc, phi and zc, then I'm sorry, again I make it psi. So actually what I am looking at is psi expressed as a function of rc, which in turn is expressed as a function of x1, x2 and x3. Of course it doesn't depend on x3, that's a different matter. And phi, and then zc expressed as a function of x1, x2, x3. Then I can apply the chain rule and get this, right? So even though I want just the operation, it's important to keep in mind that there is a scalar function, because of the functional transformation that makes the application of the chain rule more obvious. Otherwise, you're just doing in terms of the operation alone, that becomes a bit difficult to handle, at least for me, right? So this is clearly now, right? d psi by drc times drc by dx1 plus d psi by d phi times d phi by dx1 plus d psi by dzc times dzc by dx1. So now what I need is all these relations. Rc is x1 squared plus x2 squared over half. Phi is tan inverse of x2 by x1, and zc is equal to x3, right? So this would be, so I've got the derivatives d psi by drc times, what is drc by dx1? I have to calculate that, right? So it is 1 over 2 root x1 squared plus x2 squared, right, times 2 times x1. That of course finally I have to write it in terms of the cylindrical coordinates, right? For now I do the differentiation plus times d phi by dx1. So this would be tan inverse. Tan inverse x with respect to x is 1 over 1 plus x squared. So I have to differentiate this with respect to x1. So this is equal to 1 over 1 plus, I differentiate first effectively with respect to the root x2 by x1. And then I have to differentiate x2 by x1 with respect to x1. Right? So that is minus x2 by x1 squared. So clearly that is minus x2 by x1 squared plus x2 squared plus this term, so d psi by dzc will not necessarily be 0, but dzc by dx1 is clearly 0. So that's all I'm going to get. Right? So now I can write this. So 2 can be cancelled out. So this is x1 by rc and x1 is of course rc cos phi, right? So this is rc cos phi by rc, right? And this is minus x2 is rc sin phi, and this is rc squared actually, right? So what I get here is d by, effectively now I can write it in terms of the operation alone. D by dx1 is simply given by cos phi d by drc, right, minus sin phi by rc. I can write it like this, d by d phi. In important thing to remember is this is acting on a function of x1, x2 and x3. This is going to act on the same function psi expressed in terms of rc, phi and zc. Similarly, I have to express the others d by dx2. Now all that I have to do is the same thing holds. Instead of rc by drc by dx1, I will have drc by dx2. This would also be d phi by dx2, right? So I get that, and d by dx3 will simply be d by dzc. There is no. So now all I have, we have run out of time. You can fill this out. I write it in normal style. You can do the same thing. All you have to do now is to differentiate this with respect to x2 rather than x1, and then reconvert back to the cylindrical coordinate. Right? So now I have the expressions for ERC, E phi, and EZC. I'm sorry, E1, E2, and E3 in terms of ERC, EZC, and E phi. They have already written. So I put those in there, and then for d by dx1, d by dx2, d by dx3, I put these, and you have to combine everything, and it will simplify quite well to the final expression which we will see in tomorrow's class.